Okay, work, power, and energy. Let's just introduce the topic by reminding ourselves of the various forms of energy. So, we've got things like kinetic, potential. We'll come back and give some more detail about these later, but there are different types of potential. Gravitational, chemical, and elastic. As well, we're going to have things like sound, heat. We may want to call that thermal energy, light. We can say electromagnetic, so that covers both electrical and, sorry, get that right, that covers both electrical and magnetic things, because there's a very, very close interrelationship between the two forms of energy, or and even when you get into light is called electromagnetic radiation, so it's tied up there as well. And are there any others we can think of? Perhaps we might talk about nuclear, maybe. That probably covers it. I mean, you might want to say something like wave energy, but that sort of can be covered by those various things there. All right, conservation of energy, a very, very fundamental principle in physics. If you carry on to study A2 physics, you'll find there's a little bit more to the story than what we're stating here, but at this stage, we will just state this principle of conservation of energy. And what I'm doing here is, because I have great belief in the value of the dictionary, I'm just looking at the statement on page 24 of the dictionary. It says, energy cannot be created or destroyed, but it can be converted, i.e. transferred from one form to another. So I want you to look at page 24 of the dictionary and to copy out the definition of conservation of energy from there, please. Right, work. Work has a quite specific sort of meaning. Work is very, very closely related to the idea of energy. And we could say that work is done when energy is converted or transformed from one form to another. So if you can look at a situation and say energy is being converted from one type to another, then you can say work is being done. We tend to think of work in a mechanical way, and we'll look at the mechanical ideas associated with work in a moment. But a light bulb, for example, is producing light energy, possibly heat energy, from electrical energy. So there is an energy transfer, an energy change taking place. Therefore, work is being done in that light bulb, but it's a sort of be measured in an electrical sense as opposed to a mechanical sense. But that's a general principle in terms of work. Let's look more specifically now at the situation where we've got a force being applied. Work is done, the work done by a force is the product of the force and the displacement in the direction of the force. Couple of things to note there. This statement about in the direction of the force, you must include that, because there are situations where a force can be applied where no work is being done. One situation could be simply, if I walk up to a bench and I start pushing on the bench and the bench doesn't move, in other words, if there's no displacement, then there is no work done. A satellite circling the Earth has got a force of gravity acting on it. but that force of gravity is perpendicular to the direction in which the satellite is moving. So no work is being done on that satellite as it rotates around the Earth. You might like to think about that situation just a little bit more to think what that might mean. All right, so W equals F, and also notice that it said displacement rather than distance, and that's simply, at year 11 level, you would have said distance. Now we're a little bit more sophisticated in our understanding, and so we use S for displacement. All right, so here we've got a body, we're applying a force to it, and we move that body through a distance. Sorry, I said the word distance, didn't I? Through a displacement S, and therefore we can calculate the amount of work done on that body. If there is friction present, that work would be done in overcoming friction, and we would generate heat energy. If it was a frictionless surface, that work that we would do would cause the body to gain kinetic energy. So it just depends on the situation there. All right, an example. A horse pulls a barge along a canal as shown. Calculate the work done by the horse on the barge. It's the work done on the barge that we're trying to figure out. The reality is that the horse itself may do a lot more work, just generating heat and everything within its muscles and so on. But some of that energy will just be dissipated to the surroundings. We're interested here in the work done on the barge itself, and so our formula is going to be W equals F times S. But because the force acting here, 3,000 newtons, is not actually acting in the direction in which the barge is moving, which is that way. Now the barge would probably have to have its rudder turned in some way to keep it from getting pulled into the bank, I would suggest. All right, so we need to figure out the component of the force that is acting in the direction in which the barge is moving. Now I've said in our previous statement, force times displacement in the direction of the force. Here it's probably easier to work out the size of the force in the direction of the displacement. So we're going to work out the component of the force. This is the connected side, so this will be 3,000 cos 15 degrees. All right, so the work done, 3,000 cos 15 degrees multiplied by the distance traveled, 200 meters. I didn't need those units at the end there. All right, so we work that out, and you should be capable of working out the answer and working that down. Oh, the other thing we didn't mention, we should have mentioned back there, are the SI units are going to be joules. So let's just flip back to even, I'd say, that statement there about work, and say that the SI units of work, and we've come across this already, of course, in our stuff to do with homogeneity and base units and all that sort of thing. The SI units are going to be capital J, named after a scientist, be a French scientist of the name of Joule.